And welcome once again, Calculus 3 students. We are looking at section 15.7 where we're talking about Stokes' theorem, and we'll be using the right-hand rule to point in the direction that we are looking for and get that normal vector. So first up, what we're going to be trying to do is verify Stokes' theorem in example 1. In example 1, we have that the orientation of C means that our vector is normal to S, pointing in the outward direction. Now the vector field is a rotational field, so it's that A cross R, where our A is the vector 0, 1, 1, and our R is the vector x, y, z. Alright, so now that we're set up there, that means that the axis of rotation points in the direction of that 0, 1, 1 vector. And we're going to parameterize this in polar coordinates, and that would mean my r of t is going to be 2 cosine t, and then 2 sine t, and our t is going to be in between 0 and 2 pi. And we do have a circle of radius 2. Note, we're going to need to know r prime. So r prime is going to be equal to minus 2 sine t. And then for the derivative there, that's just going to be 2 cosine t. Now we're set up to find our circulation integral. The circulation integral, so my volume button goes down. Okay, the circulation integral looks like our field vector integrated with respect to r. This means by definition it's going to go from 0 to 2 pi, and we're going to dot product our unit field vector with that derivative of our r vector, and then just substituting in for our vector field and for our r prime, and then doing a little bit of manipulation, a dot product, then manipulation, then we integrate, we'll get 8 pi. Now we've got that line integral, and next thing we need to do is we're going to compute the curl of the vector field. So let's plop that down and let's look at what we've got next. So in our next little blurb here, we need to look at the surface integral, and it's going to be that cross product, and just like we did before, we're going to compute that cross product, and then we are going to go into our table and get we're going to do our change of parameters. In substituting into Stokes' theorem, we will take our cross product here and do the dot product with our outward normal, as you can see here, and then we will change the polar coordinates, and then we're going to integrate. Alright, and this is changing to polar coordinates, doing your integration, and then the result is 8 pi. In this next problem, they just want us to evaluate that line integral. So we will begin by evaluating the curl, and we start off by noting that our cross product is just going to be the same determinant that we've been doing, resulting in a vector. And this means that the appropriate vector normal to the plane is then going to be, I'm going to take those partials, and when I do this same partial that we've done before, we're going to get 4, 2, 1. And this would be an upward pointing of this normal oriented to that C. Next, I'm going to need to compute the integral. So let's write down what our result is here. So if you'll notice, we have our cross product, dot product with our normal there. And what we're going to end up with after doing this dot product and then integrating is this negative 88/3. Right, let's look at this little cap that we have here. Our function on the surface is this z is equal to 5 minus x squared minus y squared. It's chopped off here at the z equal 3 line, and we are going to figure out the value of the surface integral. So let's go ahead and write, if you would, we've got this projection downward. That's just going to be the x squared plus y squared equal to 2, just straight down, with z equal to 3. Now let's go ahead and eliminate, that is after we've eliminated z. So my r of t, or my r vector, is then going to be square root of 2 cosine t is the radius of that circle, square root 2 sine t, and then 3 for the z component. Then we'll take the derivative of our r vector. Let's also go ahead and get our partials. Alright, and just substituting in, noting that this is just that definition of my f, which is sitting up here. Notice my I component, my j component, and my k component. Doing the dot product and computing that integral, you'll get 0. In this interpretation of the curl, we are looking at a point 1/2, 0, 0 sitting right here, and we want to know which way the wheel is going to spin. Now, if the axis of the wheel is aligned with the x-axis at P, the flow strikes the upper and lower halves of the wheel, and so the wheel doesn't spin. But if the axis of the wheel is aligned with the y, the flow strikes the face of the wheel, and it still doesn't spin. If the axis of the wheel is aligned with the z-axis at P, the flow of the direction in the y is greater for x less than a half than it is for x greater than a half. Therefore, a wheel located at 1/2, 0, 0 spins in that counterclockwise direction if you're looking at it from above. Alright, to compute the graph of the curl of V, I did the cross product here, and you can note that the curl points in the z direction, and it's in the direction of the paddle wheel axis that gives the maximum angular speed of the wheel. So it is that at negative 2x. Now at x equals 0, the wheel doesn't spin at any point along the y-axis when its wheel is aligned with the z-axis. So this will give us a counterclockwise rotation. Next up, just a few final notes on Stokes' theorem, just looking at it from a different perspective, and the fact that if the curl equals 0, it implies that f is then conservative. And that's all we have for this section. Email me if you have any questions.